in the lecture last week, there were two places I got stuck, and I'd like to go through those spots again. Really, there were two equations, and I want to talk about the origin and what the significance was. The first was in the area of constitutional supercooling. Right? And we went through the discussion about that, saying, well, the concentration of the ejected element in front of the solidification front depresses the melting temperature, or the liquidus temperature. We explained that, and we wound up with the equation the temperature gradient, and the x is the direction in front of the solidification front, must be greater than the difference in the between the bulk liquidus temperature and the interface temperature divided by the diffusion coefficient and the velocity. So this is the has the units of length, and that is the diffusion zone in front of the solidification. And if you rearrange this, we'll put this over here to have d over v greater than that temperature difference. This is referred to as the equilibrium freezing range. And it's the temperature range over which you have a planar solidification front. And what's significant about this is the fact that we typically don't observe planar solidification. The only time is when you have a very special experimental setup in order to maintain a planar front. Most of the time you wind up with a cellular or a dendritic fronts. So you'll have some solid going into a liquid that has some nodules to it. You can also get dendrites in which you have solid, liquid, and you'll have tree-like structures that are growing outward. So that's the first equation that I wanted to talk about, and I was trying to think about what the significance of this was, and the significance really is that it's a limited case, and the temperature difference is the characteristic parameter. The second was in the case of normal eutectic solidification. We were looking at the thermodynamics and the kinetics of eutectic growth. So we talked about having eutectic lamellar structure, having the in front of the B region ejecting A atoms that then diffuse laterally to the alpha phase, which then absorbs them, and the alpha phase is ejecting B atoms, which I'll draws that are diffusing to in front of the beta. And we'd written out our thermodynamic expression, delta G is a function of lambda, where lambda is the periodicity of the lamellar structure. And we've got the difference in the free energy driving the solidification is a function of the difference in the free energy for an infinite separation. So this is just a system where you're creating alpha and beta, but there's no interfaces. And then we have this interface energy, which comes about from the fact we have an interface, and the spacing tells us the volumetric density of the interfaces. And using that, which we had before, is just the latent heat multiplied by the undercooling and divided by the transition temperature, in this case the eutectic temperature, and setting this equal to 0, we can solve for the critical size lambda, and we got lambda star is equal to 2 gamma Bm eutectic temperature divided by delta H delta T0. And basically, this is showing that when lambda gets too small, that means that we've created so much surface energy that we stop having any thermodynamic driving force. So lambda must be greater than lambda star if we're going to have a driving force that's pushing us to solidify. Now, thinking about this, we know that if we want the maximum thermodynamic driving force, then lambda goes to infinity. So this term goes away, but we don't observe that. And that's because we have kinetic processes in addition to thermodynamics. So if these are infinitely far apart, then the lateral diffusion becomes a problem. And this is what stops the growth. So talking about the kinetics, we have this solidification front advancing with some velocity, and the velocity is going to be proportional to the flux of atoms lateral to the surface. And that's going to be equal to the diffusion coefficient dc dx, where that's the concentration gradients that are, again, lateral to the surface. And that allows us to write the velocity is equal to some, I should call it K1, some constant of proportionality, d delta x by lambda. So delta x, that is the, well, we'll come to that, I guess, but delta x is the concentration gradient here, and that's coming from the local equilibrium in front of each of the phases, and lambda is the spacing. Now this delta x, where does it come from? Well, if we want to talk in terms of local equilibrium, we can say this region right in front of the alpha, we're going to have Gibbs free energy curves. The x-axis is xv, that does something like this. So this is going to be G liquid, G alpha, And this is our common tangent line. So we have, at that local interface, we've got alpha, alpha plus liquid, liquid. And in the two-phase region, which what we have right at the interface, this is giving us X, B, L. That is the composition of the liquid that is immediately in front of that interface. Same way, if you want to talk about the local equilibrium directly in front of the beta phase, we'll have a Gibbs free energy curve, G, XB, GL, G beta, common tangent lines, beta plus liquid, and that point is our B, call this L beta, and I'll call this L alpha. So this is the composition at that point. So that means then just that our delta X is going to be XBL alpha minus XBL beta, coming from these. So that's where our concentration gradient comes from. Now, thinking about what's happening here, we have a few things that we know. For example, we know that when lambda is equal to lambda star, this has to stop moving. It has to stop growing. So the velocity has to equal 0. So lambda equals lambda star, v equals 0. But that velocity, right here, it depends on a constant of proportionality, the diffusion coefficient, lambda, which we know has a finite value, right? It's non-zero. In fact, it's going to be lambda star, which means that this delta X has to equal 0. So that's one thing we know. We also know that if lambda goes to infinity, we know that this, it also doesn't go to infinity. It has to be finite. And what's going to happen is that as lambda goes to infinity, it's going to asymptote toward some constant. So our delta X should have, versus lambda, should have some shape that does this. Lambda is equal to 0, it's going to have this. Nope. It has to say some shape like that. So when lambda is equal to lambda star, delta X is equal to 0, and out here it asymptotes to some, what I'm going to call delta X naught. And an equation which gives us this shape is this. Delta X is equal to delta X naught 1 minus lambda star divided by lambda. And this was the equation that I was looking at the end of lecture. This is a logical consequence of the two limits of possible values that lambda can take. Now, that's one thing we know. The other thing we know, or at least what I would call a very good approximation, is that out here, this value that it asymptotes to, that's delta x naught, that delta x naught really should be proportional to the undercooling. And it's probably linear proportional. You know, worst case, it'll be slightly nonlinear, but the linearity is going to dominate. And that means that we can write delta x0 is equal to some k to delta t naught. So k2, that's just a constant of proportionality. So I can take this and put it into that expression and put this expression into the velocity, and this will give us that the velocity is equal to a constant of proportionality, which I'm calling k3, which is just the product of k1 and k2 d delta t naught divided by lambda. So that's delta x divided by lambda, 1 minus lambda star over lambda. And this is our expression for the velocity. Now, what this does is, one, it suggests that we can use delta T naught, our undercooling, as a means of controlling the velocity, but it also suggests that the velocity and lambda are independent of each other. And that's not what we observe. So why not? Well, the reason that they're not independent is because if we take our velocity, or even we just take these lambda terms, and we take the derivative with respect to lambda of 1 over lambda 1 minus lambda star over lambda, instead of equal to 0, we get lambda is equal to 2 lambda star. So the derivative of the velocity with respect to lambda, solving for lambda, gives us 2 lambda star. And that tells us that the maximum velocity so Vmax happens when lambda is equal to 2 lambda star. Okay, so what are the implications of this? The implications, for one, is that, let me erase here. Power 2. The maximum velocity is equal to k3 d delta t 1 over 2 lambda star, which can be arranged to give us that V max lambda star is equal to some constant as k3 d delta t over 2. Of course, recognizing that that constant does depend on the degree of undercooling. But nonetheless, the velocity and the width are tied together. And we also have that the max divided by delta T naught. Is equal to a constant. Squared. Squared. And the reason it's squared is that if you substitute this lambda star into lambda, there's a delta T naught there. So the point is that these are all tied together. The values of the velocity, the spacing, and the undercooling are all coupled. Now, again, most of the time, planar growth is not what's observed, right? We don't get an advancing front that looks like alpha, beta, alpha, right? We get a cellular growth. So we have a cellular growth that looks like that. And the entire length is advancing, and we have the lateral diffusion. And that means that if you want to, you could also take that undercooling and break it down into its parts. So we could talk about the undercooling due to the curvature, and due to the surface energy, right? These have to do with size effects, and we could talk about delta T D, diffusion. But we're not doing that here. So this is what I wanted to finish covering in lecture, but stopped short of.